So welcome friends. In the previous lecture, I have taken up a series of flat plates mounted on a wheel. And when the series of flat plates are mounted on a wheel, what is the force? And then what is the work done? What is the efficiency? What is the condition for maximum efficiency? And finally, what maximum efficiency you can get if you really have series of flat plates on the periphery of a wheel. So that's all what we have done. So the maximum efficiency you can get if you keep series of flat plates is only just 50%. So with that background, now I will go into, of course, the series of curved plates. If we put it, what will happen, that we will see in this lecture. Thank you. So this is the case 2, which I was talking about at the beginning of the previous lecture. So instead of series of flat plates, if we keep a series of curved plates, what will happen? So it is a series of curved plates. I can call them as veins. On the periphery of a wheel, jet striking at the center of the vein. And now what we have to do, calculate what is the force, calculate what is the work done, calculate what is the efficiency, condition for maximum efficiency, and finally, what is the maximum efficiency that you can get it. So these are the things that which we need to study in this particular class. So now if I take it, suppose again like in the previous lecture, if I take it, so this is the center of the wheel. I have taken, this is the wheel. So if you take it, I will just mark actually little bit thicker so that you can understand a wheel like. So now if I these are all the spokes of the wheel. Now what I am doing here, this is one vein like that. I have having another vein like that. I have vein like that. These are all the veins. These are all the veins, not flat plates, are all veins actually, which are mounted on the periphery of the wheel. Right now, basically, the moment the jet strikes at the center of this, right? This is the velocity of jet v, and then after striking, it goes like this. So the velocity of the wheel is u, and this starts rotating in this direction. So if I take it, basically, so now same explanation, whatever I have given in the previous thing, same holds good. That means if a velocity of jet v strikes the curved plate or vein, then naturally the way it moves forward and the next vein comes and occupies its position. Like that, the way there will be always a vein before the jet. That is number one. There will be always a jet, sorry, always a vane before the jet, right? One after the other, the veins are coming and occupying the positions. So because of that, the veins, when they are moving, actually, the wheel starts rotating. When the wheel start rotating, the wheel be rotating at an constant angular speed. Corresponding to that angular speed, let u be the tangential velocity of the vane. V is the absolute velocity of jet. A is the area of cross section of jet. So already, like in flat plates, the first thing is the mass of fluid striking per second is equal to the whole mass which is coming out of the jet nozzle, the whole jet is striking it. So that's why it is rho AV. This is the fundamental thing you should note it. Then naturally important thing is what is the initial velocity? Because when I don't mention anything, it is always x direction. Initial velocity of jet, it is nothing but the relative velocity of jet, because plate is also relative velocity of jet with respect to the vane, so which is equal to v minus u, right? So that means this is the direction with which it is, this is the relative velocity. Now next, after striking after striking the jet leaves tangentially. That means if you take this is the vein, this is how jet strikes, and this is how the jet leaves. So that's why if you extend it, so this is the tangent. And this angle is theta, right? Theta is the angle made by the jet, made by the jet with horizontal, right? And this angle, you know it, it is 180 minus theta. This is what we call it as previously the deflection angle. Next, therefore, what is the final velocity? Final velocity of jet with respect to plate in x direction. That is very, very important, in the same direction of jet. That is in the same direction of jet is equal to, right, v minus u cos theta. Why? This is how it goes, v minus u. So I want this. So this angle is theta. So it is v minus u cos theta. But now the direction of it is opposite. So this is the incoming jet, this is the outgoing jet. So if I take this component, so this is v minus u, this is v minus u cos theta. Both are opposite. So that's why I need to put minus. Therefore, applying impulse momentum equation, applying impulse momentum equation, right? Force is equal to, if I don't mention anything, it is x direction. Mass per second into initial velocity minus final velocity. So if I take it, Fx is equal to mass per second is rho AV because the whole mass is striking. Initial velocity is V minus U, that is F relative velocity, minus V minus U cos theta. This is what we call. So it is rho AV into, right, V minus U into V plus. So it is V minus U if I take common into 1 plus cos theta. So this is the first thing, that thing 1. Then what is the work done per second is equal to Fx into U. So it is rho AV into V minus U into 1 plus cos theta into U. This is number 2. Right. Then once work done is what? Work done is equal to what? Output is nothing but work done per second. So that is equal to rho AV, V minus U, 1 plus cos theta into U. 3. Then what is input? Input is equal to the kinetic energy of jet. It is half mv square. So half into rho AV into V square. It is 4. Therefore, efficiency is equal to output by input. So it is equal to rho AV, V minus U, 1 plus cos theta into U divided by half rho A V into V square. So this rho AV you can cancel. So it is equal to 2 into 1 plus cos theta into V minus U into U divided by V square. So it is nothing but 2 into 1 plus cos theta by V square. I write it as 1 into VU minus U square. For maximum efficiency, dou eta by dou U is equal to 0. Therefore, 2 into 1 plus cos theta by V square into dou by dou U of VU minus U square is equal to 0. So 2 into 1 plus cos theta by V square into, it is dou by dou U of VU minus U square. V minus 2U is equal to 0. As 2 into 1 plus cos theta by V square cannot be 0. V minus 2U must be equal to 0 or V is equal to 2U. So this is equation 5. So therefore, eta maximum is equal to 2 into 1 plus cos theta by V square into V minus U into U. This is what? So it is equal to 2 into 1 plus cos theta by 4U square into 2U minus U, single U square. So U square, if I cancel it, half we cancel it, we get 1 plus cos theta by 2. Right? This I substituted here. So this is the equation for maximum efficiency, 1 plus cos theta by 2. Now we take it a flat series of flat plates. Here theta is equal to 90 degrees. Therefore, eta maximum is equal to 1 plus cos 90 degrees by 2. So it is equal to half, it is equal to 50%. This is what I have shown in the previous lecture. Suppose if I take a series of semicircular veins, that is theta is equal to 0. The moment semicircular means theta is equal to 0. Therefore, eta maximum is equal to 1 plus cos 0 by 2. So cos 0 is 1, 1 plus 1, 2 by 2. So it is 1, that is equal to 100%. So if semicircular veins are mounted at equal distance on the periphery of the wheel, on the periphery of a wheel, then maximum efficiency we can get is 100%. But 100% is always a theoretical thing, but it may not be practicable, right? So that is why, so this is only a what you call it as a theoretical value. It is only a theoretical value. But however, in practice, what is the problem? In practice, basically, there will be loss of energy due to friction, or impact for SCTA, or impact takes place as the jet strikes the veins. So always it cannot be basically continuous like this. So therefore, for series of veins, F is equal to rho AV into V minus U into 1 plus K cos theta. This cos theta it takes care of the energy losses, which we have neglected from the beginning in this chapter. At all the places, if you remember, we assumed that there is no friction at all. So that's why we neglected that and we put that K is equal to 1 at every point. So that's you should remember actually. So now if I summarize what we have done today, if you see it, for example, in the case of a single curved wave moving, if you take it, similarly, series of curved waves moving, if we take it, then we can explain number one here. In this case, the mass is equal to rho A into V minus U. Here, mass is equal to rho A V. This is the fundamental difference. Then force is equal, force means Fx is equal to rho A V minus U whole square into 1 plus cos theta. Here it is Fx is equal to rho AV into V minus U into 1 plus cos theta. Then third one, work done is equal to Fx into U. Here also work done is equal to Fx into U. Then here basically if I take it, what is the maximum efficiency conditions? V is equal to 3U, whereas here for maximum efficiency condition is equal to V is equal to 2U, whereas here maximum efficiency is equal to 8 by 27 into 1 plus cos theta. Here maximum efficiency is equal to 100 in 1 plus cos theta by 2. If you take semicircular, eta max is equal to 8 by 27 into 1 plus cos 0 degrees. It is equal to 16 by 27, which is equal to 16 by 27 into 100. It is approximately 60%. Whereas here, semicircular, eta max is equal to 1 plus cos 0 by 2. It is equal to 1. It is equal to 100%. So with this, I will stop this lecture and we will continue the same pace in the next class with some problems. So with this, we have completed series of flat plates and series of curved plates. Both the cases we have completed. In the next class, we will take up some more problems.
Like, share, and subscribe. Hit the bell icon for more updates.